Okay, so let me welcome you to this lecture 10 of our course. In the previous lecture, we talked about infinite horizon problems, the theory, both analytical and algorithmic. In terms of the analytical results, we have Bellman's equation, convergence, that is the equation that has as unique solution the optimal cost function for discounted and stochastic shortest path problems under our assumptions. We have been talking about the two problems, stochastic shortest paths and discounted. Today we're going to focus on discounted problems. So we have Bellman's equation, we have convergence of value iteration, we have conditions for optimality, and we have two major algorithms, value iteration, and the other one is policy iteration. And we talked about the convergence properties of policy iteration with and without errors. All of this is sort of theory. Now we're going to talk about reinforcement learning built on top of this theory, and in particular, approximate policy iteration and Q-learning. And we're going to discuss centralized implementation aspects and distributed parallel implementation aspects now on a distributed system. So let me give you the outline. We're going to review some of the exact theory and then introduce some of the approximate policy iteration theory. And by the way, today I'm going to use a lot of a big part of this lecture from a video that was recorded 2 years ago. One of the consequences of this is that 2 years ago, I was using a slightly different notation. Okay, don't panic. There are only two differences in notation. Instead of using X for state and Y for next state, I'm using I for state and J from next state. This is also a very common notation, and I was using it 2 years ago, but for uniformity, I changed it this year. So the video is going to use the old notation. I don't think it should confuse you. Okay, so after an overview, we're going to talk about approximate policy iteration. We're going to focus on parametric approximation, like with an approximation architecture, with a neural network to approximate target cost functions or target policies. Then we're going to discuss Q-learning, exact and approximate versions of Q-learning. Then we're going to talk about the issue of training using least squares, and also a high-level discussion of how we bring in simulation into the picture to calculate projections. Projections on a smaller set, on an approximation architecture, things like that. This is sort of to stimulate your appetite to read some more. Then we're going to get off the video and start talking about how we use parallel computation in approximate policy iteration. There's a tremendous amount of computation involved in approximate policy iteration, training of neural networks, generating the data. So parallel computation can be of great importance in the solution process. And in fact, it has been very important in AlphaZero. It has been instrumental in the success of AlphaZero. And we are going to talk about, after an overview, we're going to talk about two aspects of parallel computation. One that does state space partitioning, state space parallelization, and the other one is based on control space simplification and multi-agent rollout. And we're going to discuss also two applications, two case studies based on recent papers. So, okay, so now we're going into a video lecture, but a facetious challenge question first. In this field, you'll hear a lot of terminologies. Terminologies are already numerous, but new ones get invented all the time, or variations of old ones get invented all the time. So I use the term policy iteration. It may be exact, it may be approximate, it may be optimistic, and so on, simplified. You'll see a lot of other terms, more anthropomorphic, like self-learning, self-teaching, self-taught, self-directed, and or you may just view it as math, okay? Just algorithmic math. And I tend to follow this particular line of particular approach and call methods policy iteration. But you may like something different. And I want to ask you, which of the following best describes approximate policy iteration? And you may write to me about it later so that in my future writings, I can make an adaptation. Okay, so end of story. And now I'm going to go into the video. So let's review some of the ideas that we have been discussing for the past couple of lectures. We consider infinite horizon discounted problems, a finite state space, states denoted by I, controls or within some control constraint set, transition probabilities, this is the basic model, cost per stage, and also a discount factor. We'll focus on this lecture exclusively on discounted problems. Everything that I'm going to say has counterparts in stochastic shortest path problems, but we're not going to get into that. Okay, the main results. Bellman's equation holds for the optimal cost function J star. It has a unique solution, and there is also a unique solution to a Bellman equation corresponding to a policy that has this solution is denoted by J mu. Okay, this is a vector of n components, one component per state. We have the value iteration algorithm that starts from an arbitrary vector J0 and generates a sequence of vectors Jk using this recursion. And with the minimization here, it converges to the optimal cost function. Without the minimization and for a given policy nu, it converges to the cost of the policy, cost vector of policy nu. And we also have an optimality condition. If mu sub I attains the minimum here for every I, then mu is optimal and conversely. Okay, so now the policy iteration algorithm generates a sequence of policies. Starts with an initial policy. Given the current policy, let's say mu k, the first phase is policy evaluation to compute the cost vector of that policy by solving the Bellman equation. Okay, it's a linear system of equations. In principle, it can be solved. And this is policy evaluation. It's this box here. Then we generate an improved policy by minimization, one-step look-ahead minimization with the cost of the current policy used as look-ahead approximation. It's this box here. So we cycle around here, generating a sequence of policies. And the property is that the convergence property is that this process terminates with an exactly optimal policy. And there is also an optimistic version of that, which does not solve exactly this system of equation, does policy evaluation by value iteration, by a finite number of value iterations for the policy mu k. Now, this will not give you the exact J mu, but it will give you something that you can still put in here in this minimization. And it turns out that this is also solid, a solid algorithm. It converges asymptotically to the optimal cost function and gives you also an optimal policy asymptotically. Reinforcement learning algorithms that use value space approximation are typically based on approximations of this process here, and they are typically optimistic. They use value iteration or approximate value iteration for generating cost evaluations. Okay, so we're getting into the familiar picture of representing approximation in value space with one-step look ahead. It involves minimization of the sum of the cost of the first step and the expected cost of the future as approximated by J tilde. And you remember that there are three types of approximations here, and they can all be more or less designed independently. One is J tilde. How do we compute J tilde? All of the ideas that we have discussed so far for finite horizon apply also to infinite horizon. And we can use problem approximation, rollout, approximate policy iteration, parametric approximation, representation of the parametric architecture here, and also aggregation, which we haven't talked about. We are going to focus on this green stuff here today, okay? And there are also approximations in the computation of the expected value, approximations to the minimization, and so on. So we're going to focus in this lecture on rollout, and particularly approximate policy iteration schemes, which operate as follows. Several policies are generated, starting with some initial policy. Each policy is evaluated approximately with some J tilde cost function. Often, and it's going to be our focus actually in this lecture, using a parametric approximation architecture, for example, a neural network. So the current policy is evaluated approximately using some kind of feature-based architecture, neural network, and so on. And we generate the next policy by policy improvement based on J tilde. OK, so we have a starting policy, a second policy, and so on. At some point, we stop, OK? And we use the last policy for one step look ahead here. OK? So that's the idea. Now, if we don't go through several policies, but just use the initial policy, this is rollout, okay? Rollout is just one-step policy iteration. Okay, so let's talk about rollout. Now, rollout, in the context of infinite horizon problems, is used in a truncated form. Because remember, rollout evaluates cost values by Monte Carlo simulation over the rest of the horizon, but the horizon is infinite, so we cannot go to the end. At some points, we have to stop, truncate the trajectories, and use some kind of approximation for the remainder. Okay? So the typical use of rollout with a given policy nu, the base policy, is to have, we are at the state ik, we use a one-step or multi-step look-ahead tree. Then from every leaf of the tree, we run the rollout policy for a finite number of steps. Sometimes fixed, sometimes not fixed, depending on the leaf, okay? And it may be also approximate in some sense, right? Some leaves may be evaluated more accurately than others. But in any case, after the rollout, the truncated rollout, we take a terminal cost approximation to compensate for the lost accuracy for the last remaining steps. So that's truncated rollout, L step look ahead, rollout with a given policy for a limited number of steps, and finally, a terminal cost approximation. Now, without any terminal cost approximation, in this ideal case, this is just a single policy iteration combined with multi-step look ahead. With a terminal approximation, it's a single optimistic policy iteration. Remember, optimistic uses a finite number of value iterations for evaluation. Okay? So optimistic is what underlies this truncated rollout. Now, in your book, you'll see performance bounds for this scheme, for the rollout scheme, single policy generated. And the performance bounds say that the performance of this truncated rollout policy improves as the bound on the performance of this rollout policy improves, as the depth of the look-ahead increases, and also as the terminal cost function approximation gets closer to the optimal cost, which is the ideal, of course. And notice that close mean close to J star here is in the sense of modulo constant shift. What happens here, you can get a very, very bad approximation J tilde in the sense of distance from J star, but if you shift everything by a constant,
then the rollout policy does not change. However, the J tilde and J star may become close. So what we mean close here is modulo constant shift. And you can look at the book and see a precise statement of this type of result. There are several results of this type. They are not, they are qualitatively useful. They tell you that you should be striving for longer look ahead if you can, and you should be striving for a good approximation at the end. So that's how you should view them. They are qualitative statements, but they are not helpful in designing specific schemes in any way. Okay. Now, for the case of approximate policy iteration, I mentioned last time the typical result and also a mathematical result and also the typical performance of this approximate policy iteration scheme. Okay, so in this figure, J mu k is the cost function of the policy mu k, and on this axis we start is the policy index, the first policy, second policy, third policy, and so on. And typically the performance improves in the beginning up until to the point where you get within a certain error zone, and then the performance of this generated policy oscillates. Okay, it goes up and down. Perhaps the same policy generated, perhaps sometimes a better policy, sometimes a worse policy, and so on. And the width of this zone depends on two parameters, epsilon and delta. Okay, delta is quantifies the approximation quality of the policy evaluation. Epsilon relates to policy improvement. So accuracy in both of those plays a role, and this is the width. It's not very exciting because there's a 1 minus alpha squared in the denominator, so this number here could be huge. But the important fact about this figure is that it represents the typical behavior qualitatively of the method. Steady improvement in the beginning and oscillation at the end. This bound is sharp in the sense that you can find an example where the bound is satisfied with equality, but typically this bound is conservative. For typical problems, the bound is conservative. And there's also a better bound in the case where the generated policies converge, in which case you lose a 1 minus alpha factor from the denominator here. Okay, we covered this last time. So now, let's go into policy iteration with parametric approximations. Okay, so here we introduce a parametric architecture for representing costs of policies. So for a policy mu and a state I, we have this parameter R that gives you the approximate cost value of I, okay? And as we change this parameter, the weights of a neural network, we change the shape of this J tilde, and we try to make this J tilde as close as possible to J, okay, J nu. Okay. So examples for architectures are linear feature-based architectures, neural networks, and other nonlinear architectures possibly. And this exact policy evaluation box is approximated so that for the current policy mu, we evaluate it approximately using the parametric architecture, obtaining some R bar here, and we use the evaluation in a one-step look-ahead policy improvement procedure to get the new policy. Okay? So how do we do this approximate policy evaluation? Well, in the usual way of training, we generate data pairs and we match the architecture to the pairs, right, by least squares. So we generate a large number of state cost pairs, IS and beta S. S here could run from 1 to millions, okay? It indexes the data point. And beta S is a sample cost corresponding to that state. And then we use least squares regression. So we fit the pairs of state and cost to the architecture in a least square sense, and that gives me this parameter R bar, which we use now in the policy improvement box. How do we generate these cost values? Well, it's like truncated rollout. We simulate a trajectory that starts at the state IS. We use mu for some number of stages, accumulate the corresponding discounted costs, and then we add some terminal cost function approximation, appropriately discounted. So this is exact, it's like truncated rollout. That's how you obtain these cost values. And this type of scheme is also described in the literature as an actor-critic scheme. The policy evaluation box is viewed as a critic. A critic, think of a theater critic that sits in the front row and evaluates a performance, takes notes, and evaluates the performance. Then publishes the critique in the newspaper, and the next day the actor goes and reads that and tries to adjust his acting in the direction suggested by the critic. So this is the critic box, evaluation. This is the actor box, policy improvement. And when a neural network is used here, this is also called a critic network, okay, in the literature. And when a network is used to implement this improved policy, this is also called an actor network. So in the literature, you'll find a lot of these combinations of actor networks, critic networks, combinations, and so on. They represent more mathematically the evaluation and improvement boxes of policy iteration.
So do you view the policy gradient method as just a special version of policy improvement? Because mostly they just talk only about the policy gradient methods in the actor-critic approaches.
There is a gradient procedure, incremental gradient, which is in the next slide for this minimization. You can do this by gradient. There is also a pure actor network, which we're not going to talk about in this lecture, but we're going to talk, it's for Thursday, okay? Where this is what people usually call policy gradient. Here there are gradients involved, but the gradients are mainly in the critic box, not in the actor box. Yeah.
So, it's a question about the general policy improvement. So, how does the current evaluated approximate cost is related with the next policy? How do we do the minimization? I mean, do we do the minimization only over the next cost or the total costs?
The way I have presented here, there's a clean separation between two different policies. The evaluation of new bar does not use any data for the evaluation of new. However, look at the possibilities here. There's a terminal cost function approximation, which could borrow data from the preceding policy evaluation, okay? Like, for example, we could use as terminal cost approximation the approximate cost function of the preceding policy. Likely it's close enough, okay? There are ways to share data, but in this slide, they're not shown. Okay, so now let's discuss this box here, various issues, this policy iteration scheme. First of all, the training problem. Remember, the training problem comes in the policy evaluation. How do we solve this problem? Well, this problem is very well suited for incremental gradient. Why? Because it involves a large sum of differential squared terms. So we can use, we can adjust, we can implement an iterative algorithm for adjusting the parameter vector, picking at every iteration a single term here, calculating its gradient. Now, this is the gradient of a single squared term. At iteration k, we pick a single index, sk, evaluate the gradient of the squared term, and move the current iterate in the direction of the negative gradient. This is the standard incremental gradient method that we have discussed for training general architectures. We just use it in this context involving state and cost pairs. So that's the way the training is done. If you have a linear feature-based architecture, this is a little easier. If you have a neural network, then this gradient here has to be calculated with this backpropagation algorithm, which is possible and is convenient both for shallow neural networks and for deep neural networks. OK, now here's an important issue. This beta sub s involves cost calculated over a long trajectory and gives you just a single data point, right? A single state, a single loss trajectory. Lots and lots of computation. However, we can reuse trajectories. What do I mean by this? Given a long trajectory for a single starting state, we can obtain a cost sample not just for this state, but also for all the other intermediate states. So we start at some state, generate a whole sequence of other states, obtain a single cost sample, and then we move to the next one, and use the tail portion of that trajectory to calculate a cost sample corresponding to I1, and so on. So we can pick up as many as n cost samples this way. Of course, as we move towards the end of the trajectory, they become shorter and perhaps less accurate. So all of this has to be balanced out in a reasonable sense, that this way that makes sense. OK, trajectory reuse, reusing the tail portions of a trajectory. One trajectory can give you as many as n data points to use here. Another major issue, very important also, exploration. When we evaluate mu with trajectory reuse, we tend to generate samples of states that are favored by this mu. Okay? We use long trajectories, obtain several cost samples from that, but they are for states that this mu likes to go to. Okay? So if this mu has some favored part of the state space, we're going to get a lot of cost samples from that favored part and not enough from other parts. On the other hand, we're going to have some overrepresented states and some underrepresented states in this least square sum. As a result, when you calculate this R bar is going to be chosen so that the well-represented states have costs that are accurate and the others not so accurate. And when you go to the policy improvement phase, you may have very serious errors. Okay. Some major problem. Policy evaluation is not done uniformly well for all parts of the state space, but it's done for some parts of the state space better than others. But policy improvement requires that you have a fair view of the potential of all the actions in all parts of the state space. Okay? So you have to deal with that. What would be an obvious remedy here? Use short trajectories, right? And many more. That's the obvious thing. There are other schemes that people have used, and we'll come back to this question. OK, about the length of the trajectories. As the trajectory length increases, then the cost sample that you have is more accurate, right? Because you're using simulation over a longer number of steps. You're not using this terminal cost approximation. On the other hand, as you add more and more cost terms in a long trajectory, there's more and more noise that's being accumulated. Okay? So this is called the bias-variance trade-off. As the trajectory length increases, there is more variance, and less bias, okay? Short trajectories, more error in the cost calculations, and less variance. Again, you have to strike a good balance between these two. All of this is an art. There's no theory, okay? This is trial and error and intuition into your problem. Making these schemes work, making your exploration, bias, variance trade-off, all these other tricks that go in here, makes getting all of this to work is a formidable task. Don't underestimate it, okay? Here is another trick to which we're going to come later. Okay, given my problem with the stage cost given by this G, we can modify this G without affecting the optimal policies or the cost evaluations in some sense. How do we do that? Introduce a cost function V, an arbitrary V, and replace this G with a G hat, which involves adding and subtracting V terms. Then if you do that, and if you look at the Bellman equation, you will see that with this substitution of the G hat cost in place of G, then the Bellman equation is going to have as solution J mu minus V, okay? So changing the cost changes the cost values by this function V, and then given that you know V, you can recover J mu, and you can also recover J star this way. However, if you do approximations of this J mu, then the choice of V is going to affect the policies that you obtain. In reinforcement learning terms, it's called cost shaping. Shaping the cost so that policy iteration becomes more favorable. How would it become more favorable? Well, if you take V to capture a lot of the nonlinearity that's inherent in J mu, then this difference may be much easier to approximate, okay? Maybe a linear architecture will do here, and in fact, you can use a two-stage procedure. First, get a good cost-shaping function, and then plug it in the policy iteration scheme to obtain an approximation to J mu this way. So it allows the use of enhanced approximations. Okay. So this is sort of a potpourri of a number of problems that can occur here. And did I forget to mention oscillations? Okay, that's another layer of difficulty here. Any questions?
Just a comment to kind of, there was work by some people in ML showing that RL experiments cannot be reproduced most of the time. I think that kind of goes into your point that many of these things require a large amount of engineering. Yeah. And so Joel Peno actually gave a talk at NeurIPS this year, essentially talking about the fact that they took huge number of RL results and tried to have grad students reproduce them, and they mostly failed. And so I think there's enough of details which wind up becoming important, and then they don't get exposed.
Yeah, and your comment points to another related difficulty here. Many people present results and evaluate methods on the basis of a few examples and a few runs of these examples. And then a lot of the insight that can be gotten from example is not portable to other problems.
Yeah, I think,
so this is a real problem in the field.
Even changing like the random seeds have completely changed.
Exactly, yeah. Change the random seed even on the same example can produce very different results, because any of these things can go haywire. Okay. So, okay. We agree. Okay. So now let's take a break, okay, for 5 minutes. And The question is, how would you introduce both exploration and trajectory reuse into policy evaluation? We talked about it a little bit, but try to think of your own schemes, okay? How would you do it? But also think about deterministic problems, okay? Much harder. Exploration deterministic problems is more difficult. Estimating Q factors in the context of policy iteration is also difficult, okay? Because again, for a given policy, you need to get state control pairs, but the policy generates only its own controls. It doesn't generate a rich sample of controls. So what would you do under the circumstances? Let's talk about that after we come back. Okay, there's no way to get around using short trajectories, okay? Many starting states, short trajectories. And therefore, you need to use a good terminal cost approximation. That becomes more important in this case. Now, there's one other trick here that which has received a lot of attention in the reinforcement learning literature, and that is the use of an off policy. Okay, what is an off policy? In policy iteration, we try to evaluate a given policy. This is called the target policy or the on policy. Now, this on policy has its own favored parts of the state space, and it drives you naturally to those parts and does not explore other parts of the state space. So an off policy is a different policy that you use for exploration. Occasionally, you follow the off policy and you go off, veer off to other parts of the state space that will thereby contributing to a better exploration of the state space. How you design this off policy is a real nightmare for a given problem. You know, it requires you to have a good view, a good understanding of how your state space looks, how your dynamics are, how the change of a policy will take you to other parts, and how do you know that you have explored everything? Okay, if you have a toy problem with like 5 states, okay, fine, or even 100 states. But if you have a huge problem, how can you tell that you have explored enough? So this is very much an art. You can try it and see if it works. Now, there's one other thing about the off policy that was overlooked in the early literature of the field. When you use a different policy part of the time, you're going to be getting a different evaluation. You're going to be evaluating, you know, to some extent your target policy for the remainder of the off policy. So this will bias your evaluation. Get better exploration, perhaps, but bias in the evaluation. It turns out that this can be circumvented by modifying. Okay, there are tricks to circumvent that. And I'm not going to get into that because it's really complicated, but that's not so much a concern. It is a concern, but not to the extent that you might think. The bias contributed by an off policy. Okay, so much for off policies. We're not going to get this into. My favorite is many starting states, short trajectories. But okay, there's a lot of literature on this subject. Okay. Yeah.
So is there any reasonable way to choose the starting states to generate the data points?
Yeah.
Like how do you choose the starting states? Like, is it better to, for example, start with some states randomly and then see which the states are underrepresented and add them to the starting?
Okay, perhaps. So problem dependent.
Okay, so usually it's just random.
People use all kinds of heuristics, like use a whole bunch of policies, run them, and get a lot of states, and you use those as starting states, okay?
There's no rules, right?
There's no rule, yeah, absolutely there's no rule, yeah. Yeah.
So I have a question. So you mentioned that the off policy design is an art form,
Yeah.
right? But mostly people just do epsilon greedy, and it may not be the best. So I was wondering, is it reasonable to think that people are, in a sense, solving large enough problems where they don't have to compare to anybody else? So if they get done, they're done, and they have Google cluster. And whereas if you spend more time designing a much better off policy, maybe you would have done better, but you are the first to cross the goalpost, so you would not have to compare anything. Because I mean, essentially in the literature, we just see only the epsilon greedy at best.
Epsilon greedy, but you can easily construct examples where epsilon greedy does not work so well. And by the way, how big should epsilon be?
And also, I mean, my question is, does not work so well is with respect to what? I mean, if you have Google cluster and you're doing 13 billion epochs,
Yeah.
it's all inefficiencies can go under that. So, because I mean, there is a proof that it will converge, right? So.
Okay. Let me give some background for the benefit of the class of what epsilon greedy means. The policy improvement just finds the greedy policy based on look ahead with the current policy evaluation, right? Minimizes. The epsilon greedy scheme chooses a policy that's within epsilon of attaining the minimum. It's a suboptimal, but within epsilon. Okay, so if you have a cost function that's very flat, then with some epsilon that looks reasonable, you can't pick up much exploration. On the other hand, if you have some cost function that rises very steeply, small changes in control can give you big changes in the look-ahead minimization, then you can get wild choices for off policy. Maybe that will work, maybe not. But to me, epsilon greedy is sort of like the luck of the draw, okay? You're rolling the dice, and you don't really know what you're going to get. Of course, you can experiment with different values of epsilon, but it may be that different values of epsilon work well for some initial states, but for some states, but not for others. So if you have a huge state space and you try this kind of exploration, you may be lucky and hit it, after a few trials and error. But in general, you may have a hard time. It's not a general procedure. It's a heuristic procedure that may work. Like a lot of these procedures are, of course, heuristic, okay? So it's one more thing to try. But there's no solid basis for it. Okay, so here we evaluate policies by approximating their cost vector. In Q-factor-based policy iteration, we evaluate approximately the Q factors of the current policy. So we introduce a parametric architecture for Q factors involving a parameter R that gives you an approximation for the Q factor corresponding to a pair, state control pair, and the given policy. And the policy evaluation portion is done by generating triplets now, okay? States, controls, and Q factor samples, okay? And the Q factor samples are generated by simulating a trajectory that starts at the state control pair, uses mu for a number of stages after the first, and then adds a terminal cost function approximation. It's very similar to the case of cost approximations. We just use Q factors, and we have to do this for state control pairs as opposed to states. The training problem is very similar. Okay, we have state control pairs and corresponding Q factor samples, and we match them together in least square sense and find the parameter R bar. Obtaining R bar, upon obtaining R bar, then we can obtain an improved policy by this simplified minimization. Okay, this may be a simpler minimization than the look-ahead minimization that involves transition probabilities and so on. This approach also tends to be more model-free, okay, because this cost can be generated without a model using a simulator, and this minimization can be done here without the transition probabilities. Okay. Okay, a few comments about model-free policy iteration. First of all, trajectory reuse is more problematic in Q-factor evaluation. Why is that?
Because you don't see all the action, state action pairs, right? You only see one.
Right. For a given policy, you use an arbitrary state action pair in the first step, but other than that, you use the policy mu afterwards. So it's very biased towards the current policy. And it doesn't explore other controls other than those given by the policy. So, okay, this is stated here in cost evaluation. Each trajectory generates state controls pair of the special form for every stage after the first. So other state control pairs are not adequately explored. So that means that you should be using short trajectories. There's no way around that. You'd have to include in the samples a rich enough set of trajectories that start at pairs IU with U other than what's given by the policy. Now here's an alternative approach, okay? This is approximation in value space combined with approximation in policy space. We use a model-free policy iteration for cost functions. We can do that because we don't have to do any minimizations. We just run the policy, and this can be done in a model-free fashion. And then after we obtain this expression, then we take the corresponding Q factor and we approximate that with a second sampling process. So we build an approximation, a Q factor approximation using samples from the cost function approximation. Okay? So it's approximation in Q factor space on top of approximation in cost space. And this is well suited for model-free implementations. Of course, it requires a second least squares fit. And there's more possibility of error, but it deals better with the exploration issue because approximating cost vectors is not susceptible as much to the exploration issue as approximating Q factors. Okay, so we're going up the ladder in approximation, difficulties, things that can go wrong, and I wish you all success with your. These schemes do work, but it takes, for many problems, but it takes a lot of experimentation, it takes a lot of time, and also some luck. Okay, so we're done with approximate policy iteration. Now let's talk about Q-learning.
Guys, I want to take a small break to ask you for questions. Are there any questions on the video that we have watched so far? Okay, so I think there are no questions, so we'll move right along.
Q-learning is an important concept that came around in the late 90s. It sort of gave a different perspective in the field. And the initial Q-learning algorithm involved lookup table representation, no parametric approximation. By lookup table representation, I mean every state control pair has a value, okay? The Q factors are represented by a table that gives the values to the corresponding state control pairs. So we try to evaluate the exact optimal Q factors, and we do this by a form of value iteration. Okay, the value iteration for Q factors takes this form here. I've written somewhat abstractly. This F here, F of Q, is given by this minimization expression. The point that we made sometime, well, perhaps in the previous lecture, or 2 lectures ago, is that this mapping here is a contraction mapping, and value iteration converges to Q star, the optimal Q factors. So the value iteration algorithm is this, and Q-learning is a takeoff on this implemented by simulation by iterating on a single pair IU at a time. Ordinarily, value iteration iterates on all the Q factors. For all pairs IU, Q-learning operates on a single pair, okay? There are asynchronous dynamic programming concepts regarding value iteration, which tell you that you can actually implement value iteration in a very flexible way. Implement it for some states here, for some other states later, and mix them up and do it one state at a time, and it always works, okay? It's just the nature of the algorithm, and this is due actually to the contraction property, contraction and monotonicity property that's inherent in this algorithm. So fundamentally, Q-learning uses asynchronous dynamic programming ideas, and it's basically value iteration, but one pair at a time. And also with randomization, because in Q-learning, these transition probabilities are not needed. Instead, we use only a sample using transition probabilities. So let me describe this. It generates a sequence of state control pairs. And I'm sorry. You give it a sequence of state control pairs, an arbitrary sequence of state control pairs. They don't have to be generated in any way that's connected to the transition probabilities. Just an arbitrary sequence of state control pairs, and for each one, you generate a successor state according to the transition probabilities, and then you update the Q factor of this chosen pair using a step size. Okay, you go in the direction of this expression here. The details are here, but the idea is that you make a stochastic update to the Q factor of just this pair here, and you leave all the other Q factors unchanged. So in particular, this expression here is this for the target pair, and it's the same. It doesn't change for the other pairs. Gamma is a step size here. And so this is a stochastic algorithm. Why is it stochastic? Because you generate a successor state according to these probability distributions. And the successor state ends in these calculations here. So it's a stochastic iterative algorithm with a step size which is diminishing for convergence of the algorithm. And you can prove with a long technical proof, a substantial proof, you can show that with lookup table representation and under the proper conditions for your sample selection and for the step size, the choice of step sizes, you can show that the generated sequence of Q factors converges to the optimal Q factors. Now, this algorithm has very, very nice theory, but it's not useful in practice. Why is it not useful in practice?
Because you can't generate an infinitely long sequence of...
I'm sorry?
You can't practically generate an infinitely long sequence of state control pairs.
Too many state control pairs, yes. Yeah, if you have a large problem with zillions of states and zillions of controls, the number of pairs is even more zillions, and how can you store all of this into a... Okay, you can't even store the results of the computation. It's impossible. So Q-learning in its theoretical form is an algorithm that is sort of for homework problems, but not for real problems, real practical problems. Now, this algorithm, however, has been used as a starting point for approximations. Introduce approximations here, introduce approximation there. I'll give you an example, and actually this example algorithm has been used quite widely, but it's as flaky as they get. Okay, there's just nothing that you can prove about it, and so many things that you can go wrong with it. Okay, so this is the algorithm that I'm going to present. There are many variations here. Okay. We introduce a linear parametric architecture of this form. So this is a feature-based architecture with features depending on state control pair. So we parameterize Q factors this way, and we're going to calculate approximate Q factors, in other words, find R, so that this thing here is close to the optimal Q factor. That's a nice thing about Q learning. It doesn't aim for the Q factor of a policy. It aims straight for Q star, or an approximation to Q star, the optimal set of Q factors. Okay, this algorithm is called SARSA. It's a state action, reward state action. I think that's the name of the algorithm. It's quite popular. And there are several versions of it. I'm going to give you the simplest version here. Of course, with different variations, you may get better performance. This is the most optimistic version, where you change your policy after every iteration. Okay, so now notice that for every parameter value, there's a corresponding policy that's obtained by minimization here. So at the kth iteration, we have the current parameter vector, we have some state ik, and we have a control uk that we have chosen in a greedy way that I'm going to discuss shortly. We simulate the next transition using the transition probabilities of the current control. Okay? Then we generate a new control that we are going to use at this new state by minimizing the corresponding Q factor. Essentially, with a change from ik to ik plus, essentially we're using the policy that corresponds to rk, okay, to generate a new control. And okay, there may be, to enhance exploration, you may use an epsilon greedy type of control. And now, with the new control as chosen, you calculate in the new state, you calculate an update to the current parameters that involves this term here. Okay, gamma k is a step size parameter. This is the feature vector corresponding to ik and uk, and there is this qk term that's called the temporal difference. Temporal differences are an important concept in reinforcement learning. We're not going to discuss them very much, but they are important. Perhaps we're going to say a few more things about them in the next lecture. Now, this qk corresponds to the estimate of Q factor at time k minus the future Q factor, okay, at next state, ik plus 1, with the control uk plus 1, and this one stage. So this is like a residual in Bellman's equation. Current Q factor minus discounted Q factor at the next state control pair minus the one stage cost. And this can also be viewed as a gradient in some regression, underlying regression. And that's how the algorithm works. So at every iteration, there's a new RK vector, and there's a new policy that's being used to generate controls. And you keep going like that, and okay, something happens at the end. Sometimes it works. People have had success with this algorithm in problems that are not insubstantial, but I'm sure there have been many failures as well. There are all sorts of technical issues here. How do you pick the step size? How do you do the exploration? And so on. Okay. Okay. So this is a sample of algorithm. And let me also mention a multi-step version that involves updates of the policy after several steps. Give some time to the method to settle down, basically to slow it down. This is the extreme optimistic version and the most likely to fail, actually. Okay. Now we move to the last topic for this lecture, a high-level view of least square straining. I'm going to bring in the idea of implementing projections using simulation. It turns out that policy evaluation with a parametric approximation architecture corresponds to finding some vector within the manifold represented by the approximation architecture. And what better to do than to project, orthogonally project on that manifold? It turns out that least squares is a form of projection. That's the point of view we're going to discuss here. And we're going to bring this, we're going to take this as a starting point for other methods, not just the training methods that we have discussed so far, but other methods that have received quite a bit of attention in the literature. For example, there's a lot of literature on temporal difference methods, TD methods. And TD methods can be viewed as policy evaluation type methods with simulation-based projection. So I'm not going to go into all the details of this. It's a very fascinating subject. There's a lot of interesting theory around it, but we just don't have time to cover it in depth. However, your book has a section on this topic that you may read as an introduction to further reading, okay? Just to give you some language and some conceptual framework to go with. Okay. So we're looking at approximate policy evaluation and a projection view of that. So we have Bellman's equation for a given policy. And suppose we introduce a parametric architecture involving a parameter vector R. Now, this defines a manifold over which all of our approximate vectors lie. Okay? Maybe a linear manifold for a linear architecture or a nonlinear manifold, like in a neural network. A neural network would have a horrible manifold, and your approximation vectors are going to lie on this manifold. So this is what we call M here. And we have J mu, and somehow we want to squeeze it onto the manifold. That's what we're trying to do with policy evaluation. So a common approach, very common in numerical analysis that goes back to God knows when, maybe Gauss, maybe before that, is to project on the manifold of the approximation architecture. And this is the notation I'm going to use. The typical vector J is projected onto the manifold by finding the vector V, which is at minimum distance from J. Okay? This is called the projection. And I'm going to be using a Euclidean norm, but weighted, okay, with weight parameters psi. These are positive weights, and I'm going to actually use weights that add up to 1, so they form a probability distribution. So that's a common way of approximation, and you can think of 3 general approaches for approximating the cost of a policy using projection. One is we have this manifold, M, and we project J mu onto the manifold to obtain this projection. And we use the projection in place of J mu. The second is, it's like truncated rollout. We start with some approximation J hat of J mu. We perform n value iterations on that to obtain this. Now I'm using here abstract notation because I just don't have enough board to put it. So this is the result of n value iterations corresponding to mu, starting with J hat. And then we project onto the manifold this result of value iterations. And then we use this in place of that. This is pretty much what we have been doing so far, it turns out, with truncated rollout and the approximate policy iteration scheme we have been used. Okay, so that's one scheme. A second scheme, a third scheme, is to take this Bellman equation and consider a projected version of that and solve the projected version. Now that's different than the other stuff. It's not like this. Here we project J mu. Here we project the equation and solve the projected equation. Okay. Does this make sense? Well, okay, first of all, J mu, because the projection will lie, the solution here will lie on the approximation manifold. So it makes that sense. And this equation is something like Bellman's equation. It may or may not have a solution. We don't know that. Temporal differences methods are based on this third type of approximation. They introduce a projected equation and perhaps with some lambda parameter in here, which I'm going to discuss perhaps in the next lecture. And there are methods for solving this type of equation. And by the way, this third approach is not a quickie approach that just came up in the last few years. It has a long history in numerical analysis. It's called Galerkin approximation. It's a general method for approximating the solution of systems of equations. It's used very extensively in partial differential equations, in multi-grid approaches where you take a problem that's defined a continuous state space or a very dense grid and they approximate the solution on a lower dimensional grid. A lot of these methods are based on this approach here, Galerkin approximation. However, all of these methods do not really apply to our context. Why do they not apply? Why doesn't this apply? Suppose I give you mu. Find me the projection of J mu for a given value. How would you do that? Well, you have to know J mu, right, to project it. And you have to know values of J mu to project it. And we don't know that. That's what we want to find, right? Now, this is a little bit more applicable because it doesn't require that you know J mu. All it requires that you are capable of doing value iteration on some J hat that you know. So this is a little bit more, looks like it's more feasible. But still it has problems. Why? For a large problem, okay, this projection is just impossible to perform. And the only hope is to approximate it by simulation. And that's the direction in which we're headed. And about this, the same problem again. For a large problem, the right-hand side cannot be evaluated exactly. But again, there are ways of doing it by simulation. And that's where a lot of the theory and the mathematically interesting theory in reinforcement learning comes into play. So perhaps I'll get into this subject next time, but I'll give you a bird's eye view of how these projections can be implemented by means of simulation. Okay, so we consider a manifold of this form, a linear manifold, a subspace involving a feature vectors phi. Okay, so phi is a matrix that's long in rows, short in columns. Every row corresponds to a state, and the row is denoted by so, and it involves the features of the state. Okay, so phi I prime is the feature corresponding to the ith state, and there is this phi matrix, and it's multiplied with R to give you a long vector that's going to be it's going to be a potential approximation to the cost of policy. And so this is a subspace spanned by basis functions. The basis functions are the columns of phi. Each column is multiplied by the corresponding coefficient of R. Okay, so how do you calculate the projection of a typical vector J on this subspace? Of course, we have to solve this least squares problem, and using the form of this weighted norm, it's a least squares problem, right? Projection is a least squares problem with weights psi I, the weights of the norm, and we're trying to match to find a phi I prime R that is close to the state J. So the minimization is over R here. Okay? So this is a linear least squares problem, which has a nice closed form solution. The solution is like so. So projection is a least squares problem and has a closed form solution, provided that your manifold is a subspace. Okay. Of course, the problem in calculating this is that you may have a lot of states, and then this vector is a column vector that's very big, and this is a row vector that's very big, and doing this, calculating this matrix is a task that you cannot perform for a large problem. However, here's how simulation will work. Suppose that the xi's define a probability distribution. They are positive, and they add up to 1. Look at this term here. Does it remind you of something? It's an expected value, right? It's an expected value of this vector with respect to this distribution. Being an expected value is great for simulation, okay? You can approximate expected values by sampling. And that's how we are going to approximate this term here, by sampling. And this is also an expected value, right? It's this thing here weighted by probabilities. So we view these two terms as expected values, and we approximate them by Monte Carlo simulation. And the Monte Carlo simulation works as follows. You generate sample states according to this psi vector, okay, because we want to emulate this probability distribution, and we form these estimates. So this is the empirical estimate of this matrix product, this sum of outer products, and if you do things right in Monte Carlo simulation, this thing is going to approximate this, generate a lot of states, calculate the sum, divide by the number. This is a Monte Carlo estimate, an empirical estimate of this matrix. How about this term here? We also view it as an expected value. Now, one of the problems that we may be facing is that we may not have exact values of J. So you need to sample J also. Now, suppose that you sample J with some zero mean noise. So beta sub S is a sample of Ji sub S plus some zero mean noise that, okay, the noise has to satisfy some condition, which makes this relation true here. So with Monte Carlo sample, we approximate this with that, we approximate this with that, and we obtain an approximate projection, phi r bar now, where r bar is given by this matrix here. So that's the Monte Carlo approach for doing projections. And now here's another thing. Okay, so here's the estimate, the Monte Carlo estimate. We see that this same estimate is obtained by a least squares minimization. This least squares minimization involves, if you solve this, you get this as a solution. Does this remind you of something? We've been doing things like that all the time, right? We calculate state cost pairs, and we've been fitting them together in a least square setting. So simulation-based projection can be implemented in two equivalent ways: replacing expected values in the exact projection formula with simulation-based estimates. This is this type of solution. And the second is to replace the exact least squares projection. Okay, remember that the least squares projection is this. We replace this with a simulation-based estimate also. And it is this minimization. So all these minimizations that we have been doing, all these training problems that we have been solving, we've been doing projections actually on some approximation manifold, be it nonlinear in the case of neural networks or being linear in the case of feature-based architectures. And there's some other interesting things here. There is some art involving implementing this kind of simulation-based projection. However, it is not necessary that the sampling is done independently. You obtain independent samples. In the case of reinforcement learning, you almost never get independent samples, but it's not necessary in this methodology. What you need for these to be faithful estimates that converge to the exact quantities as the number of samples increases to infinity is that the empirical frequencies by which the indices appear in the simulation sequence are consistent with the probability psi. In other words, the psi weights determine the empirical frequencies by which you should be sampling the different states. On the other hand, you don't really need these probabilities ahead of time. You just design a reasonable simulation scheme and let the probabilities become whatever the simulation dictates. In other words, implicitly, the simulation determines the psi. So all you have to do is have some kind of a reasonable simulation scheme, generate your samples, use this formula, or solve this problem here, not in closed form, perhaps iteratively, and then you have obtained a projection. Now, if you go back here, that's how you'd project the cost of a policy onto a manifold. Get samples and do a least squares fit. That's how you would implement the training process of truncated rollout or approximate policy iteration. You generate samples of this, and you put them into a least squares training problem to obtain an approximation onto your architecture. And it's similar also to this type of projected equation approach. Can implement this approximately by Monte Carlo simulation.
Okay, guys, that's the end of the video. And I'm going to switch to slides. Okay, so now we're going to turn to issues of computation and fast computation. We're looking at this approximate policy iteration diagram that we have seen before, where we use approximation in value space to evaluate the base policy, and we use this evaluation in policy improvement, and then we approximate the policy that we get by policy improvement, which is the rollout policy, and we obtain an approximate version of this policy through this policy network. Now, all of this requires a lot of computation for offline training and also for online play. Even if you get the final policy, you still have to implement it. And the collection of the training data may require lots of simulation, computation, training of the neural, using a training algorithm, which may be slow. We have the issue of exploring adequately a large state space, which means more simulation samples, more data that you have to collect from the entire state space, and in some equitable way to enhance exploration. And then after you have obtained the final policy from this approximate policy iteration, you do online play, online implementation of the policy that of our rollout policy by using whatever you have obtained here as base policy. And this requires minimization, which may be difficult, truncated rollout, which involves a lot of simulation calculations, and all of this under tight time constraints. For offline training, we can train for days and weeks, right? It's offline. However, when it comes to online implementation, there are usually some time constraints between stages that you have to produce a control. You have to calculate a control in between stages. Now that may be 1 second, 1 minute, 1 hour, or maybe a few microseconds, okay? So all of this is very important and for implementation purposes, and doing the calculations fast can be very important in both of these contexts. So the obvious answer to speeding up computation is parallelization, using a parallel computer that can parallelize operations. And there are many of those parallel operations that can be performed. And now we're going to ask the question, how do we use parallelization in rollout and approximate policy iteration? So we'll take a break here for 5 minutes, and I want you to think about all the possible ways for doing parallelization here, and also in one step, look ahead, minimization and approximation with value space. Where do you see opportunities for parallelization? And I'm going to let you think about that for 5 minutes, and then we are going to discuss various possibilities. I want to ask first about this parallelization. What do you see as possibilities? Give me an example, the simplest example, where we can use parallelization in this landscape here of rollout and approximate policy iteration. Any suggestions?
Can you break the state space up into regions and perform all your computations in these individual regions and then aggregate them somehow?
Yes, that's one possibility. Do separate computations in different parts of the state space with different processors.
Yes.
So you can break up your state space with 10,000 processors, let's say, and construct 10,000 neural networks. That's a lot of neural networks for value and another 10,000 for policy. And then have them combine the results and even communicate interim results. That's a possibility, and we're going to discuss that. Are there any simpler possibilities that you can see? Okay, well, actually, I can see 4 possible types of parallelization. The first 2 are trivial, okay? Very simple, unsophisticated, just a very naive application of the concept of parallelization. The other 2 are more sophisticated. The first one is Q-factor parallelization. Think of rollout, or think of approximation in value space in general. At the current state, the one-step look ahead does a separate Q-factor calculation for every control. And then we compare those controls. That's how rollout works and approximation in value space more generally. Well, the calculations for each control are entirely independent of the calculations of any other control. So all of them can be executed in parallel. All the Q factors corresponding to a state with all the different, for all the different controls can be done in parallel. So if you have n possible controls to choose from, you can use n processors to do this calculation in the time that you need to do one calculation. So that's fairly simple, and you should do it every time you can do it. Another possibility is Monte Carlo parallelization. A lot of our calculations involve Monte Carlo simulation, like Q-factor calculations for stochastic problems. They involve Monte Carlo simulation. We just roll out a policy with obtain a lot of stochastic samples, and then we average them. Now, Monte Carlo simulation is a perfect example of efficient use of parallelization. You have to calculate zillions of samples, but all the samples can be calculated independently of each other and then averaged at the end. So that's another naive kind of parallelization, which, however, is very useful. And you should do it every time you have a parallel system that you can use. Now, here's a third type of parallelization, which we will call multi-processor parallelization. And this is along the lines of the question that we had just a little while ago by Jameson, I believe. We use a state space partition. We partition the state space into subsets, and we execute separate value and policy approximations on each subset. And we do this in parallel, but the calculations are coupled in the sense that Okay, these policy approximations and value approximations should communicate with each other in order to generate complete trajectories. So here we break up the space and we deal with a large state space. The other type of parallelization is multi-agent parallelization that we have dealt with earlier, which deals with large control spaces, in particular, the case where the control consists of multiple components and the number of Q factors increases exponentially with the number of agents. And here's the maximum number of possible values of UI. We have seen this situation, and in multi-agent parallelization, in multi-agent schemes, multi-agent rollout, for example, we do this minimization one component at a time, one agent at a time. This reduces a lot the amount of calculation. And we have also discussed schemes that involve some autonomy with this, these signaling schemes to parallelize the calculations of the agents. So what we want to do now is focus on these two, which are non-trivial, and discuss them, and also give an example of each one. Okay, first, state space partitioning and distributed training on each subset of the partition. We have gone through this picture before. The idea is to partition the state space into several subsets and construct a separate policy and value approximation in each subset. Now, when we were discussing approximation architectures, we said that it's not a good idea to introduce a regular partition, like a grid-like partition of the state space. Rather, it's better to partition the space of features and then introduce the partition that's induced by the features, so that states within each subset of the state space partition have similar features. Okay, that makes sense on a number of ways, and but it's not going to be important for our discussion here. We just assume that there's a partition, and the fact that you may be using features to generate the partition is not going to be material. What we're going to focus on is how we implement truncated rollout and policy iteration with state space partitioning. So there's a fairly obvious idea of doing that. We have a partition of the state space, and we assign one processor to each subset of the partition. And each processor uses a local value and a local policy approximation only within its own subset. Remember, the value functions are functions of the state. The policies are functions of the state. So a local value and a local policy is a cost function restricted to the processor's own subset. So each processor has a piece of the value function and a piece of the policy, and communicates with the other processors whenever they need some information about the values of from other subsets. They communicate with the processor that controls the subset to get the corresponding information. So there are local calculations and on occasion exchange of information as needed by the algorithm. So each processor updates values locally on each subset. For example, it does policy evaluation for the value network by value iteration, and also updates policies locally on each subset by doing policy improvement. Possibly using also multi-agent parallelization, although multi-agent parallelization is not going to be material to this concept here. And now the processors communicate asynchronously to the other processors their local values and policies as needed. Now, the computation is asynchronous because some processors may compute faster than others, or may have more states to deal with than others. So all of this is rather chaotic, but I'll give you a picture on how it will work shortly. But before we get into that, this obvious algorithm fails, and fails under relatively simple conditions. There's an old example by Williams and Bird that dates back to almost 30 years ago, which provides an algorithm without approximations, the lookup table case, and also deterministic example, simply asynchronous computation. And the algorithm gets stuck and does not converge to the optimal Q factors in this particular case. Now, there is a fix to this algorithm, a different algorithm that does not have this problem. There is a paper that I wrote about 10 years ago, a series of papers rather, with my former student, Jenny Yu. And we have an algorithm that corrects this difficulty and proves convergence rigorously for our lookup table representations of policies and cost functions. This is a non-trivial type of proof and analysis, and I'm not going to even attempt to go in there, but there are references that you can consult. This algorithm also admits, in principle, neural network approximations, although the results are more sparse in this particular case. We just have some error bounds. Is this correction needed? It's not very clear, because usually this algorithm actually works. It is only on the rare cases and maliciously and artificially constructed examples that it can fail. So even though this analysis here has broader implications within the field of dynamic programming and reinforcement learning, in the example that in the case study that I'm going to show you shortly, we have not used this algorithm. Instead, we have used this simpler algorithm. So let me get into an illustration of how state space partitioning in parallelizations will work. Okay, so here is a state space, the square here, and we have a partition into 5 subsets, and we have 5 processors. Each processor computes a piece of maintains a piece of a policy and a value function, a cost function, defined over its own subset. So this processor has the value function and updates it within this subset, and does policy evaluation and policy improvement in the context of policy iteration. And there are 5 processors, and each one does the same thing. However, to do the rollout process, the policy evaluation process, what do we do? Let's focus attention on this processor. This processor picks initial states, sample states, and then runs simulation trajectories. Now, these simulation trajectories use the local network, the local policy network of this processor, the current policy, up to the point where we cross into a different processor's territory. Once we go in here, we don't know how to proceed. So what we do is we use the local cost function of that processor, which is communicated, perhaps asynchronously, to this processor. So these red dots here are the points where we cross into other processor subsets, and we obtain as terminal cost approximation what is supplied by the local value network of that processor. To obtain this value over here, we obtain the local value approximation of this processor, and so on. So it's local simulation using the local network. And once we cross into other subsets, we use the values of other processors, which have to be communicated. It's not a difficult scheme to implement. All you need is to do the same thing that you would do with a single processor, and then truncate the simulation once you get into another processor's territory. So we start with some base policy and a value network, base policy and a value network for each set. We obtain a policy and a value network for the truncated rollout policy using values supplied by the neighboring networks, and then we repeat. And so we generate a sequence of local values and local policies, and that gives us, and that can be patched together in the end to produce a global cost function and global policy. And incidentally, I'm not going to spend much time into this, but we have observed, and it makes sense, that by partitioning the state space, you can control better the issue of exploration. Remember, exploration of the state space requires that you get balanced information from all parts of the state space using the current policy. You have to explore the entire state space more or less evenly. And by partitioning the state space, you tend to help this process because you can localize your search into different parts of the state space in a natural way. Okay, so I'm going to leave this at that. And we're going to look now into a case study. This has to do with a pipeline repair problem, a difficult problem as it turns out, involving partial state observation. And this is from a paper from with 4 other co-authors, Sushmita Bhattacharya, Sahil Baidial, who's our grader, as you know, Thomas Wheeler, and Professor Stephanie Gill. And this is from last year. And the problem is one that involves 20 locations along a pipeline arranged linearly, which are potentially damaged. They may have some damage. We don't know how much damage they have, except probabilistically. So some sites have a lot of damage, some sites less damage. Some sites have very slight damage, and some do not have any damage. However, the damage of each location is imperfectly known, and it changes with time. It evolves according to a Markov chain. So all we know for each location is the probability distribution over the 5 levels of damage. So the states, the number of states here, aside from the location of the repairman who moves around back and forth trying to repair the damage, aside from the location of the repairman, the number of states are all the combinations of different damages, 5 levels of different damage along 20 locations. And so that's 5 to the 20. And it's about 10 to the 15, if you'd like to think in terms of powers of 10. This is a humongous number of states. And the actual state space here is far worse. It's the set of probability distributions over these 10 to the 15 states, okay? So it is the set of belief states over this finite but very large state space. So what the robot does now is decides at each stage whether to move right or left. And when he moves to a location, it inspects its location. It can inspect its location and then it fixes the damage if there is a damage. Otherwise, he can just rush through and go to another location that perhaps needs damage more urgently, needs repair more urgently. So that's the trade-off in each decision of the robot. Either neglect to look at a particular location and move forward towards another location that has higher probability of damage, or stop, inspect, and then spend one stage time to repair the damage. So essentially, the trade-off is between repairing even small damages or rushing forward towards the more urgent damages, or what we think are the most urgent damages, because all we have is a probability distribution over the levels of repair. So now we have implemented this approximate policy iteration. We have implemented rollout, and rather successfully, but we wanted to do a full-fledged policy iteration, and we wanted to test also this idea of state space partitioning. And we partitioned the state space into 6 pieces involving 6 policy networks, and we need only 3 value networks, it turns out. And the partition is done on the basis of features. We classify states as being in 6 different categories. One category is there's lots of damage to repair in the aggregate, and most of the damage is to the left of where we are. Another category is damage is in the aggregate. There's a lot of damage to be repaired, and most of the damage is somewhere near where we are. And the other one is when most of the damage is to the right. And now, so these are 3 subsets, which are further divided into 2, depending on whether there's a lot of damage in the aggregate to be performed or not. So these are the 6 subsets. And the 3 value, we need only 3 value networks because, once we cross into a region of the state space where there's little damage to be done, then we can perform a full-fledged simulation without the use of a value network from other sets of the partition. Okay, so here are the results of the experimentation. There are a lot of details in this implementation. Details that have to do with the neural networks. These were neural networks, by the way, that were trained with TensorFlow, I believe, off-the-shelf software. There are issues of how many sample points you use, how many layers you use for the neural networks, how many nonlinear units you can use for each layer. All of this, how do you do the exploration? There's all sorts of issues here that took a lot of time to resolve. It's not a non-trivial implementation. However, what I want to show you is the range of results that we have obtained, starting from some base policy. The base policy is you go to the nearest damaged site, a site that has some positive probability of some repair, of needing some repair. And you go to that. So if that is to the right, you go to the right. If that's to the left, you go to the left. And if you reach a site that is damaged, no matter how severe the damage is, you repair it. That's the base policy. It's somewhat intelligent, but not all that hot, okay? All that impressive. And here is the cost that we obtained by simulation, of course, because it's a stochastic problem. Here's the cost that we have obtained with this base policy. And you see 3 bars here. The blue corresponds to parallel computation, state partitioning with 6 policy networks and 3 value networks. The red corresponds to using only policy networks and no value networks. So in this case, the simulation was done all the way to the end, and we did not need any value network for terminal cost function approximation. Finally, the yellow corresponds to centralized computation. No parallel computation at all. Just a single policy network, nothing else. Now, here you see the results. Let's focus on the yellow, which is the ordinary policy iteration without any parallelization. It exhibits the kind of behavior that is sort of typical. The first few iterations reduce the cost. So going from the base policy to the first policy, this is the rollout policy, okay? Corresponding to this base policy, we obtained an improvement. And then with the second iteration, which is rollout using this one as the base policy, we obtain further improvement and further improvement and further improvement. Now, here we obtain steady improvement. But if we were to continue with more iterations, you'd see that we would reach a plateau and then we would be oscillating. That's the general character of approximate policy iteration without any further structure. So without parallelization, it's the yellow bars here. With policy network parallelization, it's the red bars. A little worse, but not that much worse. However, much faster, okay? 6 times faster when it comes to policy improvement operation. The blue bars give you the results where you have even more parallelization with 6 subsets and 6 policy networks and 3 value networks. This is the fastest of the 3 because we have the most parallelization. And the cost is not that much deteriorated relative to the red calculation and the yellow calculation. Now, our paper has a lot of details about how the implementation was done, what the choices were, what the pitfalls were, and also some comparisons with other state-of-the-art methods, which actually work very poorly on this problem. This is a challenging problem. It's simple to represent it, to give a picture of it, but when you comes to solve it, it's extremely difficult to solve it. And the state-of-the-art software for it did not work well at all on this problem. In fact, they gave results that were worse than the base policy itself, which is kind of disappointing. However, we did much better, and that's what we found. And you can find, again, you can see the results of the experimentation in the paper. So are there any questions that you would want to ask me or Sahil about this case study? Any details of the implementation that you may be interested in?
I have a question about how you divide the state space. So you said that you divide the state space where you collect states that have similar features together into one section or region, correct?
Right, yeah.
Okay, it seems to me that states with similar features, they're not necessarily near each other in the state space. You may, in order for example, if you're in a region where all of the states have similar features, to get from one state in that region to another, you may have to go through many other different regions according to the transition probabilities just to get there. It seems like maybe in general, that's sort of a strong assumption that that states with similar features are necessarily close to each other in the state space. Yeah.
Well, here we used very few features, right? We used the feature of lots of damage to the left, or lots of damage to the right, or lots of damage in the center, or little damage, and most of it to the left, or to the right, or the center. Okay, so these are very simple features. We could have used more features, in which case we would have a finer partition of the state space, possibly. But we do use features here. And it is true that there are heterogeneous states within each partition, each subset of the partition. For example, the location of the robot is not specified. So for example, there may be locations in, there may be states in the first subset of the partition where the robot is over here or also over here. Obviously, these two states are going to be quite different. So there's a lot of differentiation of states, but it's with respect to the features that we have selected to use. We could have used more features, but we elected not to do that because it's just too many neural networks to train, okay? Does this answer your question?
Yeah, I think so. So I guess my more general question is, how do you decide or compute the boundaries in your state space? And it sounds like it's just really problem specific, but maybe there are some more general rules.
Well, it's like, how do you generate features, okay? The features are problem specific unless they're automatically generated through a neural network. Remember, we had two different ways of calculating features. One was to look at the problem and decide what's important, what are important characteristics of the state based on our experience, based on some preliminary computations. And the other is when we ignore the other extreme. We ignore the features of the problem. We give up on trying to figure out on our own the features of the state. And instead we use a neural network, which both calculates the features and the weighting of the different features. So here we did not use the neural network for that purpose. And also, if you use a neural network to construct features, you may also use simultaneously features that are problem dependent. However, in this particular case, all the features were problem dependent, but they make sense, okay? I mean, if you look at this problem, obviously, a good feature is to know which part of the pipeline is the most damaged, okay? Relative to the location of the repairman. And also whether there are lots of damages all over relative to few damages. That's also an important feature, heuristically, okay? So you did hit on a particularly sensitive and important issue. How do we select features? And a lot of, on a given problem, a lot of the success that you may have hinges on being able to select nice features and be able to reduce essentially the dimension of your problem to a lower dimension. So that's all I have to say about the features that we have used. Sahil, do you want to add something here?
Yeah, I want to ask.
Sorry, yeah. Please go ahead, yeah.
Okay, I want to ask a question. How many data points you need to evaluate for each iteration? It seems the damager of the number of the damager is 10 to the power of 15, and the number of the state for the robot is another 10 to the power of 15, right? So how many Can you give me a magnitude how many states you need to evaluate for each iteration?
Yeah, that's a good question. Sahil, do you want to take that?
Yeah, sure. Yeah. So for this problem, we had to first sample initial states from which we can kind of run our methodology. So we use around 200,000 training samples, and out of those, 10% were used for evaluation for all these networks, policy networks as well as value networks. On this particular case, which is 20 damaged locations and 10 to the power 15 states. So that's the number, 10% of 200,000.
Okay.
All of this is empirical, and it's hard to know when you have sampled enough, okay? Let me add this. Any other questions? Okay, let's go now to control space parallelization and multi-agent rollout and policy iteration. Okay, we have discussed this earlier in the context also of simplified minimization in approximation value space schemes. One agent at a time for the case where there are multiple components, multiple agents. And this minimization is done one at a time in a given order. We select an order and we do the one-step look ahead of each agent in sequence. This reduces dramatically the cost of policy improvement, but it is an inherently serial operation because each agent needs the rollout control of the preceding agents in the order. So agent number one computes and finds its control at a given stage and state. Then the second agent computes to find its own rollout control, but it needs the rollout control of the first agent, and so on. So the preceding agent's controls in the order are needed to calculate the rollout control of a particular agent. So how can we parallelize that now? Well, we have discussed this in the context of, in a previous lecture, 2 lectures ago, I think, by using pre-computed signaling. In other words, in order to, the main problem with parallelization is that to compute the kth agent rollout control, we need the rollout control of the preceding agents. So suppose we use pre-computed substitute guesses in place of the preceding rollout controls. Instead of waiting for this to be computed, we use guesses, these mu hats of x. These are functions of x that are pre-computed with the help of a neural network or something like that. So what are the signaling possibilities? One possibility is to use the base policy controls for signaling. And I have shown you a demonstration of this where it works very poorly. It can work well for some problems, but in some other problems, it can work horribly bad. The other possibility is to use a neural network representation of the rollout policy controls, whereby we pre-train a neural network to emulate this rollout policy, and we use that in the context of online one agent at a time computation, which is done simultaneously. Okay, so there are other possibilities also for signaling, and our paper, which I'm going to show shortly, has several of these possibilities involving delayed communications of rollout controls between agents and so on. So let me return to this problem that I have discussed, and I showed you some videos a couple of lectures ago. And this is from a fairly recent paper, Sushmita Bhattacharya, Shiva Kailas, Sahil Badial, Stephanie Gill, and myself. And the case study for this for this paper was this network of damaged sites, 32 potentially damaged sites, and 4 agents, 4 robots that go around and repair the damages. And the damage level of each site is unknown, except when a robot goes there and inspects it. And it deteriorates according to a known Markov chain unless the site is repaired. So again, we have a POM-DP. We have a partially observed problem, with the belief state being the probability distribution of damages, the joint probability distribution of damages over all the sites. And also, okay, the location of the robots are known. The observations here are the inspections that are done by the robots, which are used to update the belief state together with a Markov chain that you have assumed. Now, the control choice of this robot is to inspect and repair a particular site, which takes one time unit, or inspect and move to a neighboring site. The state of the system is a set of all robot locations plus the belief state of the site damages. And the stage cost of each unrepaired site depends, this is the cost per stage, right? It's the sum of the cost of all the sites. And it depends on the level of the damage of the site, with obviously more damaged sites costing more to be left unrepaired. And for this particular problem, after all is said and done, there are 10 to the 30 states, 10 to the 7th controls, and approximately. But of course, the true state of the system is much larger because it involves the belief states, the belief distributions over these 10 to the 30 states. There is some structure that's helpful here in the sense that the probability distribution of the different damage levels at each site are decoupled from each other, although in a more difficult version of the problem, this decentralized version of there would be a more centralized version of the belief state, whereby there would be correlations between the damages of neighboring sites, for example. Okay, so now we have applied policy iteration with multi-agent parallelization, not state space partitioning, no state parallelization, just agent parallelization. And I'm showing you the approximate policy iteration result with using a policy network. There's no value network. It is policy network to represent a current policy, but there's no partitioning. There's no partition of the state space. Just a single policy network to represent the current policy. And that's what this says here. There's a policy network that's used to represent a policy generated by policy iteration. And of course, the training has to be done offline with generated data and neural network training and so on. And what I'm showing here is the results of approximate policy iteration for 2 problems. The blue problem that involves 8 agents. The red problem that involves 10 agents, okay? And the base policy is go to the nearest site. Each agent goes to the nearest site that has some damage, some positive probability of damage. After one iteration, we get a reduction, a very substantial reduction. Incidentally, all of this policy iteration is multi-agent, okay? This is multi-agent policy iteration with neural network approximations for the policies. So for both the red and for the blue problem, we get reductions. And if we were to continue for more iterations, We didn't run too many iterations. Each iteration costs a lot of time. We're talking about hours of computation. And we would have had oscillations here. And I think perhaps we have run made some runs with more than 3 iterations. And the results are typical. However, the method is successful. And when we compare it with the alternatives, the state-of-the-art methods that are available, are published, we find that our method works much better, but also that the other methods just don't work for this problem. They do worse than the base policy, or perhaps comparably in some cases. Some of them work horrifically poorly, okay? Which is, okay, a warning that just because some piece of software has been published and the authors advertise good results with the examples that they chose to present, that doesn't mean that it's a trustworthy method. Very little that's guaranteed in this field. And you have to pick and choose how much faith you can place in different software that are available. So this is what we have obtained. And as I said, the performance here is typical. The cost improvement tails off and ends up in an oscillation. Okay. So again, there are a lot of implementation details here. Our paper contains a lot of discussion and also comparisons with different signaling policies. The signaling policy here is training neural networks to represent the rollout policies of other agents. So are there any questions here?
I'd be interested in hearing how would you apply techniques discussed earlier in the lecture regarding exploration for the case in which we don't know the Markov chain that determines the dynamics of the problem? Specifically in this case, the evolution of the node damage levels. Like, would you use model-free approach, try to estimate the model, or how would you approach that?
Well, with great difficulty, okay? Exploration has to do with selecting the training set from one policy to the next. And now, if we said the problem with the naive form of exploration, if you use just trajectories and data that is generated by one policy, that may not be a good training set to train the next policy. So one has to explore and obtain a representative sample set of states. Okay. In our case, we used, I think, Sahil may give some more details, but we used a scheme that's heuristic, whereby we combine samples from different policies. In other words, given the current policy, we generated sample states that are visited by that policy. And then we added some more. And that's why we were generating more policies. We added sample points generated by these new policies and dropped out some of the samples from earlier policies. So our sample set consisted of a mixture of sample points obtained using different policies. And the details of that are kind of opaque. It's not easy to come up with a perfect scheme. You just try some scheme that makes some sense, and then you try to improve on it by trial and error. And that's all I can say. There's a lot of literature, by the way, the reinforcement learning literature, including recent, but also from the past, that has to do with sample reuse, trajectory reuse. There is people talk about buffers where they store their samples and they replenish the buffer once in a while. There's also quite a bit of analysis that people try to do, but all of this is imperfect, okay? There's no good answer to the question of exploration in approximate policy iteration. And you might say it's the Achilles heel, the point of vulnerability, the point of greatest vulnerability of approximate policy iteration. Okay, so that's all I can say about exploration. Sahil, do you want to add something to that?
Yeah, I think what you said was correct. We used like a few samples, like typically around 30% of the training samples were generated by some previous, say, rollout policy, for example. And the rest of them were just randomly chosen from, using some random number generator. So yeah, we wanted exploration, but we also wanted to have states that are closer to the previous states. So yes, it's a difficult subject to talk about, but yeah, this is how we did it. Yeah.
Are there any other questions? Okay, so let me go to the last slide. In the last part of this lecture, we focused on distributed reinforcement learning. And it's motivated by the fact that it is a very computationally intensive methodology, and distributed asynchronous computation is an obvious answer. And it's important to identify methods that are amenable to distributed computation. And rollout is one of those. Multi-agent parallelization is a possibility for rollout. And also, we may use some pre-computed value approximations and policy, and represent the base policy with policy networks to parallelize all of this operation. Now, there's one thing that I want to impress on you, and I really believe that. And okay, different people may have different opinions and different experiences, but in my experience, as I look into this landscape of reinforcement learning methods, there's only one type of method that I have found to be reliable and consistently give you reasonably good results, and that's rollout. When you try to go into approximate policy iteration or other methods, you use, for example, repeated rollout, okay, you're talking about a different level of difficulty. And when you add partition architectures, multi-agent parallelization, all this other stuff, local value and policy networks, okay, it's an ambitious kind of methodology, but it's also more complicated. It does exploit reasonably well parallel computation, but you're talking about a more complicated methodology because it's also more ambitious, has the potential to give you better results. As you saw from these case studies, by doing approximate policy iteration, we were able to reduce the cost generated by rollout. But this can also fail far more easily than this. There's another type of parallelization that if you look back to the lecture where we talked about applications to discrete and combinatorial optimization problems, multi-agent parallelization is very much applicable to these. Okay, there are opportunities there, but we just don't have time to discuss them. And needless to say, there's a lot of things that we don't understand about both centralized approximate policy iteration and also distributed versions. And the analytical challenges are significant, and the implementation challenges even more so. But remember, there would be no alpha 0 if there was no parallel computation. So that's an interesting thought to keep in mind. So that's the end of the lecture. And in the next lecture, we're going to talk about different kind of methods than the ones that we have been talking about in the past, always in the context of infinite horizon problems. The linear programming approach, which we're going to discuss briefly, approximation in policy space, and policy gradient methods. People use these a lot. So I want to discuss the basic principles of them, and also methods that instead of using gradients, they use random search. And I'm going to use, in part, video lecture 10 from the 2019 ASU course. So you may review that as preparation for next week's lecture. And I know that several of you are immersed into these projects that you have. And I want you to know that you can reach out to me if you have questions, or you're getting stuck, or you're not quite sure how to proceed, and so on. So that's it for today. And we'll see you next week.